Okay, we are back to talk about the circuit. You will not see a big schematic. A big schematic will be too difficult to follow. So I'm going to talk about the circuit, each part, as we go along. The first we're going to talk about is the voltage divider. The divider is controlled by this button. As you can see, it will pick up. Each one can be set at different range. The divider is only divided by 6 or divided by 3, automatically pick up by the MCU. So let's take a look at how the divider looks like. We have all seen voltage dividers drawn like this, with a resistor up at the top and a resistor down at the bottom dividing the voltage. But this is fixed. I want something adjustable. So my circuit is actually looking like this. In drawing it this way, it's a little easier to conceptualize. And the resistance ratio I need is 4 to 1 to 1. So this adds up to be 6. When I'm connected down here, I will have 1/6. That's my divider by 6. When I'm connected up here, I'm at 2/6. 2/6 is 1/3. That's my divider by 3. When I'm up here, like this figure shown, I just have a bunch of resistor to ground, and it is not dividing any. This way is easier to conceptualize. Laying it sideways is easier for me to hook up. With a 2-pole 3-throw switch. At the top, the 3 resistors are in series to ground, and then this top position here and this bottom position here. The exact 4 to 1 to 1 is not a standard value, so I'm using 820, 220 and 220. The resistor here in combination is 1.26 meg to ground. On the other pole, it goes to the digital lines at the MCU for it to detect what the setting is. If I detect nothing, it's not divided by anything. If this one goes high, which would be divided by 3, when this one goes high, I'm at a divide by 6. So that's how the input circuit for the divider look like. The multiplier have similar setup, but a complication is that I also need to run it in inverting mode to support the negative value. So let's take a look at how the circuit would look like. Again, I'll lay it out the way we normally see it. This is how we normally look at a multiplier. A resistor here, and then a larger resistor to ground. And this is the RF and this is the RG. And I have, again, a setting. When I go to this setting, all these resistors just go to ground, and I'm in voltage following mode. When I'm at this setting, these 2 resistors gang up as the RF, and this one go to ground. So I'm at a different multiplication factor. So there are 3 of them there. Down at this bottom one, these 2 gang up as RF, and this one become RG. So the circuit look like this. This is the input. When I'm at this, I'm at voltage following. When I'm at this, these 2 gang up become 24, and this one is 1, so is 25 multiplied by 25. When I'm at this setting, these 2 gang up become 12K, so it's 12 to 13, almost a 1. That will give me roughly about a 2x multiplication. It's actually 2.08 when you do the arithmetic. So this is how my multiplier works in the positive mode. The inverting look almost exactly like this figure, except instead of the plus going to the input, for inverting multiplication, the plus have to go to ground. So somehow I have to flip the input around. It either go to the voltage input or goes to ground to do inverse multiplication. So in flipping the input alone, I can do inverting. And that's the job of these two buttons. Ideally, these two buttons should be a 3-pole 2-throw switch, but I couldn't find any of them at a reasonable price point. So I decided to use a pair of 2-throw 2-pole switch and just push them up and down at the same time. With the extra pole, I drive an LED, blue for minus and green for plus. So the three of them, multiplication, division, and the sign adjustment to flip the input, together form the input circuitry. So the multiplier, divider, and sign control flipping the op-amp input, all three things together forms the input circuitry. Very little protection on the input except a decoupling capacitor. It first goes into the voltage divider as we depicted earlier. If the button is up, the voltage divider goes to the plus input. This guy goes to ground because it is a 2-pole 2-throw. So the multiplier circuit, this bunch, would have this side going to ground and this side going to the divider. Now let's say the button is now down connecting to here. The voltage divider setting at no division, at minus, the division doesn't work. It goes into here, and because it is down, goes straight into the inverting multiplier. So this guy now connects to the input, and the plus, because it is down, is now connected to ground. So the input of the op-amp switch around. The second one really is to create an input to the MCU to say that, okay, I'm set to minus right now. That's why ideally it would be a 3-pole 2-throw, but I couldn't find any at reasonable price, so I just used 2 of them and pressed them up and down at the same time. And there's a total of 1, 2, 3, 4 channels. So they are address line, digital line 8, 9, 10, and 11. This one, when it go high, is digital 6, 7, 4, 5, and when this key is pressed, it's digital 2. Why did I call this an address line? Because with 5 on each, and 5 here, 5 times 5 is 25. I don't have 25 digital input here. So I'm organizing it like a square of 5 times 5 and scan through it. This is digital line 8. So I scan through it by turning this one on and the other one's off. 3 by 3 is good enough representation. The sign here just have 2, not 3. It's a 2-pole, 2-throw. When 8 is on, these 2 are off. All the connections connected to the MCU together. But when this one is on, this 2 doesn't get any current, so it doesn't go that way. Only this one is detected. When this one is on, only this one is detected. When this one is on, only this one is detected. But that was my first mistake when I made it this way. The error is, if both of them are set at the same, when this address line is on, it will feed the current back to this guy and detect the other thing, detect the other switch. So it took me a while to figure out the best way to handle it is to put some diodes there. Here you see a whole bunch of diodes. 25 of them to be exact, 5 times 5. When digital 8 is on, these two are off. Digital 11 and 12 is not shown here. The current go here. Let's say this one is pointed this way. Come down, no problem. When this one is on, let's say this one is off, no problem. Let's say this one is on, the current flow here. Going here, down, and the digital 2 can detect it. But this time, when this one is on, the current cannot backflow back to this guy to feed it. So it is organized as a 5 switches, 1, 2, 3, 4, 5, and 5 of this line, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So it's organized by 5 to detect. All the switches here on multiplier at maximum are connected to digital line 5, I think. All of them. They're connected to digital line 5. On the middle setting, they're all connected to digital line 4 with a pull-down resistor. So this way, the program scans through each of the digital line, 8, 9, 10, 11, 12 being the keypad. And when 9 is on, all these other guys are off, so only this function. And the diode there blocks any current backflow. If I am to do it again, I may want to use a multiplexer to split the digital line, but I realized I made a mistake only after I soldered everything on, so I patched on a board to add those diodes in. Figuring out how to solve that, I was quite pleased. So with this bunch of switches and this bunch of diodes controlling the input and flipping the op-amp input, the op-amp output goes straight to the MCU's analog digital converter. No magic there. Very straightforward. The MCU is just plain vanilla connection. You can get this off the Arduino website. They should agree. If not, take that one, not this one. I may have transcription error if there's any disagreement. With 5x5, I need 5 address line and 5 data line. That leaves me with 2 extra. So digital line 13, I hook it up to an LED to show me, and so I can test the MCU with the blink and other standard Arduino tool. So this LED is connected just like an Arduino board. A tag switch for reset that connects to the reset button with the 10K pull-up. The MCU's pin 2 and 3 connected to the FTDI RS-232 board actually is missing. Okay. This is my homemade Arduino. The board is right here. I took it off this one already, but I hadn't put it back in. So it just go back in there that way. And with a little retainer that I made, so here we go. Now we got RS-232 connection back there. That little FTDI breakout board connect to RX and TX. Pin 7 go to V+, and pin 8 of the MCU go to ground with another decoupling capacity here of 0.1 micro. 9 and 10 go to the crystal, 16 MHz crystal, with a pair of 22 pico, which in turn go to ground. On this side, pin 13, as I say, is connected like a regular Arduino. AVCC for analog is connected through another decoupling capacitor to power. AREF is not connected. I'm using internal reference, and it goes to ground. And analog 4 and 5 goes to SCL and SDA, which drive my little LCD with an output here and 5-volt ground output here, so I can connect up my little LCD. This LCD, when I run it faster than 0.5 seconds, it's very difficult to see. That's why the LCD is updated at half the rate of records sent to the PC. So that's how that is connected. All the other digital line just go straight to this control switch through the diode here, and the analog just goes straight to the op amp. There's no decoupling capacitor between the op amp and the analog input. There are decoupling capacitor here, however, for the power. This board actually has two voltages that it needs. 5 volt goes to the MCU, and about 6.5 volt go to the op amp. The reason is I want the op amp to be capable of outputting a full 5 volt to the ADC, so I need this to be over 5 volt. And these are the two. One is an LM317, the other one is a 7805. The 7805 supplies the MCU. And the connection is pretty much straight out of the spec sheet, except I have an input capacitor here that is 220 micro at 50 volt, an output capacitor to help the transient response, and the output capacity is 47 micro. The 220 here is selected specifically because a couple of my power bricks is not very stable. The 220 seems to solve the problem. You may not need something this big. The 47 here is really just what I have at hand. They are both connected to a heatsink. I need a power brick that is more than 8 volts so that this guy can supply about 6.5 volt to the op amp. Most of my power bricks are in the range of 12 volt to 15 volt. So I need this, although it doesn't draw a lot of current, it drops a lot of voltage. From 12 to 8 is a 4 volt drop. From 12 to 5 is a 7 volt drop. Even though it doesn't draw a lot of current, with that much drop, it gets pretty hot. So I have heat sinks on both of them. The LM317, which is adjustable to about 6.5 volt for the op amp, goes through a 180 ohm. To a 2K, and this is the variable resistor trim port that I use to adjust the voltage for the op amp to output 5 volts to the MCU. This little pin header here gives me access to AREF, the 6.5 volt, the ground, and the 5 volt. That way I can do some adjustment here. When I connected up this FTDI board, I made sure that the plus 5 is not connected, so the USB would only power this board, given that the USB power supply is not connected to the rest of the board, just the FTDI. I can get away with internal reference alone. For the following few things, since it is more important to know it happens than to see a video clip of it happening, in the interest of time, I'm using video slides. Something interesting that was causing me a lot of headache during calibration, and it took me a while to notice the issue. Right after you flash the MCU, the ADC readings differ slightly. What I've seen is a 25x multiplier. Typically, the difference is around half a millivolt to a full millivolt, but at times it goes up as high as 5 millivolt after multiplication. There's about 40 microvolts to 80 microvolts and up to 400 microvolts before multiplication. Also, the same thing happens with RS-232. With the USB already connected, there's a difference before and after the program opens the port. The difference is about the same half to 1 millivolt. I'm not sure if it is because of my DinoMeter design or the MCU itself. A power cycle immediately after flashing or after port open solves that. If you plan to measure low voltage, you should check your MCU's behavior after a flash and before and after RS-232 port opens to understand its behavior. By not connecting the FTDI board's 5V, and since the MCU is internally powered, it worked well even with internal reference alone. It even eliminated issues when using a different PC with a slightly different USB voltage, some a little over 5V and some a little under 5V. However, there's another issue, grounding. When USB is connected, there's another ground path established. When measuring very low voltage, establishing another ground path with USB introduces a sub-millivolt difference. When using the 25x multiplier, this may be anywhere from 0.5 millivolt to 3 millivolt, depending on what ground path we had before. 3 millivolt may not sound like a lot, but measuring current with a 0.1 ohm shunt, that is a 30 milliamp difference. So the system is designed to accept an offset, but the best bet is keep the connections consistent and get the best ground path like during calibration. Actually, this board performs a lot better than I had hoped. Since this is a learning project, I was prepared for this to not work at all. My requirement was for this to measure over 100 milliamp at 1 to 2% accuracy. Actually, I can get down to 30-40 milliamp at better than 1% accuracy. And all the way down to single-digit milliamp, the reading is good, meaningful. And even down to sub-millivolt, this one is giving me some meaningful reading. So I'm fairly pleased with that. Although having to work at it for over 2 months, most of the time was spending in calibrating this little guy. And during the calibration cycle was when I discovered some of my software problems. So, although I'm kind of DinoMeter out by now, I learned a great deal, and now I have a lot more respect with working around millivolt. I knew working with millivolt is tough, but I didn't experience it directly as much as I did in making this board work. But it's a fun project. I learned a great deal of lessons, and I hope the lessons will be beneficial to you as well. And I hope you will leave comments that I can learn from as well. And thanks for watching.